last time we had gone a lot over this average reward setting for continuing tasks where we defined this new objective that's different from what we had had before, which is the discounted reward, where we had this sum over rewards or going forward in time, but there's some discount rate gamma that ends up making so that this sum converges to a finite value. And now, if we have a continuing task, the point is it could go on for an infinite number of steps, which here is represented by this h, or sometimes it's like some horizon value. And here, instead of discounting, there's this approach where we take this average of the rewards, and we take the limit as h goes to infinity. This quantity is computing the average, but in order to actually use this practically, there were a number of other conditions we had to apply, namely that there's some expected reward value that as you go further into the future, that we can stop considering the sum of all the individual rewards and just replace this with a long-term average of the reward. So this is saying, like, under some conditions we can forego actually computing this average, like for an infinite number of time steps, and there will be some other way of figuring this out. And in particular, this distribution mu is sort of a new thing introduced, which is the steady state distribution of states. And if in fact this exists, meaning like as we go through a task and regardless of wherever we start, we go infinitely far into the future, there will be some expected probability of being in every state that will actually converge. And then, if you think about like all of these rewards, then these rewards come from state transitions. This is an average through time, and these are probabilities across the state space. So the main idea is that if this distribution exists, then we don't have to care about the time component anymore, and we can just sort of wait. Like this quantity here is this basically like what reward we would expect for making this transition, and then we weight that by the probability of being in every state. So sort of at a high level, without deriving anything, that's why this expression equals the average reward, is that we are replacing this average through time with this average across the state space. Where now, but we have to understand the probability weighting on every state to do that, which, previously, like this is a new concept. So now we have this quantity, the average reward, but clearly if we're going to use it with this equation, it depends on the steady state distribution of states. And then I wanted to show again these grid world examples. I'm hoping I need to make this wider so I can actually see what it looks like. But remember that we had these, like this was one of the grid world examples we had used for the tabular problems. And here this is a continuing task. Now this type of grid world example doesn't have to be a continuing task. When we introduced it, it was an episodic task where you would start at some state like here, and then there's a goal state, and the episode ends when you reach the goal. So if you set this up where there's like, let's say there's a reward of like 1, like here, there's a reward of 1 for reaching the goal. So if you do that as an episodic task, then you have to use Um, or I mean, whether you do that as an episodic or a continuing task, if the reward is one when you reach the goal, then you have to use a discount rate because if you don't use a discount rate, then at some point in the future you reach the goal and you get a reward of one. And that will happen regardless of how long it takes. And typically with these problems, we want to find something useful, like for a grid world, it's usually we want to somehow minimize the number of steps to reaching the goal. So this is now set up as a continuing task so that every time we reach the goal, the state gets reset back to the start, and then the task can continue on from there. So that's one way of setting this up as a continuing problem. So and this is showing a solution using a technique from before with policy iteration. And this problem is stochastic because there are these wind values. Like the reason why you can't just step directly over into the goal is because there are these wind values along the grid here that will push you up. I think the value is like 2 here and 1 here and 0 back here. So if you just try to go in this direction, you end up getting pushed up and then you have to wrap around. And so, that's a way of making the policy not quite as straightforward. If I disable the wind like here, although doing this is going to screw up something else because it's going to make something else not converge. But you'll see that then the optimal policy, wait, I have to, sorry. The reason why this isn't working is because there's another piece of this that relies on, whatever. Okay, I'm not gonna, I think there might be an earlier part where you can turn the wind off, but okay, so for this problem, there are these wind values that perturb the movement. And as a continuing task, we need some discount rate. Now, what we had seen last time is how, for this like stochastic problem, the solution seems to depend on the discount rate, right? So like if I change this to like 0.99, these values are going to change. And what is being shown here, which we don't have to compute this for this tabular solution, but this is showing that steady state distribution that I mentioned before, which is important for the average reward. So we can sort of see how the policy changes by seeing what the steady state distribution is. So like if I make this discount rate, let's say 0.5 instead, we can see there's a different solution. It's still going to the goal, but there's a different distribution now of the visited states. And this is a problem where it's a continuing problem. We could use the average reward for this problem, but we can also use a discount rate like this. And when we use the average reward setting, there is no discount rate. So, there's just going to be a single policy that we find. And we know that since if this is a continuing problem like this, we can't actually, set the discount rate to 1. So you'll see, even if I start making this larger, like I'll make it closer and closer to 1, and these values start to diverge. Now, like they should stay finite for any value of gamma less than 1. But like numerically, eventually this is going to get difficult to deal with. Now, what seems to be the case is that as I make this gamma, arbitrarily close to 1, this distribution is converging to something. And what I'm showing down here is, what we talked about it last time. I'm not going to go over it, but you can also do this sort of policy iteration with the average reward. And this is computing like the exact solution, right? There's no approximation here. Like it's using all of the probabilities. And here, like this is what the steady state distribution should be for the optimal average reward solution. And you can compare it like the two policies, you can see like it's not matching exactly yet. Like there are still some differences in the policy here. But we can tell from the distribution, that this actually is approaching this value. But the last meeting I had said how like this is sort of confusing as to why the discount rate matters because there's an argument in the book about the discount rate not mattering for these types of problems. And actually, that's not really what the book says. I'll go to this part of the book. There's this proof in the book about, if we try to optimize this, so what this quantity is, it's using the steady state distribution. And this is saying, well, what if we do compute the discounted values with some gamma? But the thing we're trying to optimize is this quantity. And this is really like the average discounted value across the states. But notice that now, like this average, we're weighting it by the steady state distribution. Like this seems like a pretty reasonable thing to do. And then it turns out that if you try to maximize this objective, then like this quantity depends on the average reward. And there is this factor of gamma here, but this factor of gamma will be the same for any policy that we look at. So the conclusion is that, optimizing this is equivalent to optimizing the average reward. And the claim is that then the discount rate is sort of irrelevant for ranking policies. And that is true if this is the objective that we are optimizing. But this is not the objective that we had looked at before. Because, the objective we looked at before, and let me see if, sorry, I had something written down. Or maybe it's just in these notes here. Mm, wait, hold on. Okay, I had it here. So remember that before we were trying to, find the optimal state value function where we had, this discounted sum of rewards, G. And when we get an optimal policy, we have a policy for which all of the state values are at their maximum value. So for any alternative policy, the state values that we find will be lower. So, there's no need to actually consider the states separately. Like, what's handled in the book here, where we're doing this sum, this is now weighting states differently. And the whole reason we introduced this probability weighting on the states is because if we're dealing with approximation where we can't actually compute a value for every state, we can just, sample the states in some way, then we can't use the previous objective because we can never actually check all the state values. We can't use any of the techniques that were in the previous section. So what we're instead doing, like even though here, like we're imagining using this objective for any problem, but the only time we actually need to use this objective is when we have these, when we're using approximation, right? Because with approximation, well, I guess that was introduced in the previous chapter actually, but we were, minimizing now this thing called the value error. Sorry. right? So the value error here, right, is where we had to introduce this steady state distribution because we have some approximate value function, and the approximate value function can't have a distinct value for every state. So we are using the steady state distribution to weight the importance of different states as a way to tell the approximation function, well, you should have lower error for the states that appear more frequently. So if you look at this grid world problem, if we were forced to approximate this instead of having separate values for every state, the error would be lowest, like in this set of states, right, where the probability of visiting them is highest. And then for these black states where the probability of visiting is 0, their value doesn't actually matter at all in the case of approximation. So yeah, it might, like, the whole reason why this other objective was introduced, this J, is because this objective is relevant to the case of approximation because we're sort of forced to use this, but previously we weren't forced to use this. So, this whole argument might not be relevant for problems where we don't have to use this. But it is still confusing because it seems like this objective is pretty reasonable. And if you compare it to what we did before, where the optimal value is actually going to have the optimal value at every state, you could sort of replace this with just a sum over the value, right? Because if we get the optimal value function from before, that optimal value function should actually have, should maximize the sum of all the state values, right? Because maximizing the sum of all the state values will be the highest when all of the state values are individually maximized. And yet, like, we can see, so using this objective, we know the discount rate doesn't matter, right? And in average reward, we don't even use the discount rate. And then if you look at this example, it seems like, well, the discount rate does matter, but as it gets closer to 1, we end up matching this objective. And and you can actually prove or sort of sketch out a proof that shows that in the discounting case, if you take the limit of the discount rate approaching 1, then you end up, like, all of your solutions end up converging to the average reward solution that we see here. Another way to have this problem is, I said, like, this is formulated in this case as a continuing problem where there's a reward of 1 for reaching the goal. But when we originally did the grid world problem, we did it as an episodic problem where there was a reward of -1 for every time step, right? So this example is actually showing the same problem, but there's, the episode actually terminates when the goal is reached. So that's why here, like, it's showing the state value here is actually 0. And then there's a reward of -1 for every time step. And in this case, we can actually set the discount rate at 1 exactly, right? Here, we can approach 1, but I showed you, as if you make the discount rate 1, then this, these quantities all diverge. If we treat this as an episodic problem, we can actually set the discount rate at 1. And then if you compare the solution, these are exactly the same solution, right? And then these numbers here represent the negative expected number of steps to reaching the goal. So at least for this grid world example, like, the average reward solution where you get a reward of, some positive constant reward for reaching the goal, should be equivalent to this formulation of the problem where you set the discount rate at 1. And again, this is only possible when we have an episodic problem. So, if you're doing episodic problems and you have, but you have to make sure that the reward scheme for the episodic problem actually makes sense. Like if I kept the reward the same as this, there's just a reward of one for reaching the goal, then I could set the discount rate at one, but that wouldn't, that would just make every policy have the same value, right? Because every state would just have a value of one because there's no discounting. So, you have to set it up differently where you get this sort of, where the reward, instead of being a reward, it's actually a penalty. And the goal is to terminate the episode as soon as possible. However, even in the episodic problem, right? Like I can set the discount rate at one, but if I change it again, just like before, the policy actually changes. And you can see like this policy is not staying the same. And this is, no longer even the continuing problem. And even like the way this policy is changing, isn't even, it doesn't even match exactly, like if I set this at 0.8, does this look, well, actually in that case, it does look kind of similar, but you'll see like, depending on what the discount rate actually is, the continuing problem, won't even match the policy here. So even though it seems like we've set up like a very, sort of neutral situation where we have a reward of -1, and we're using some discount rate, but it seems like it should still favor solutions that have, the lowest number of steps, just like we have here. But clearly that's not happening, or something else is changing. And I had sort of, posed this question before last time, or I wasn't exactly, I mean, I had some idea of what the reasoning is, but I didn't have a great explanation for the whole thing. But now I think I have a better explanation of what's actually happening here. And let me just show this and see if it makes sense. So in the grid world example, we have an environment where there's states and there is some goal state, right? And I had set it up in the episodic case where there was a reward of -1 per step. And then it terminated at the goal. And here we know that this is just the definition of the value function. So, right, it's just the discounted sum of these rewards. In this case, they're all -1. So we just have this sum over gamma. And, this, where the sum terminates is just where we expect, like from a given state, how long we expect it to take to reach the goal. So then, let's say we have the undiscounted case, like I had just shown. So gamma is 1. So if gamma is 1, you can look at this sum, right? And you can see that, this is just the sum of 1 from 0 to n-1, which is just the same as the n value, right? So here, the values should just be the expected value of ns, where this is just the number of steps. And we seem to have something which matches what the average reward, what we would expect from the average reward setting, right? Where here the average reward is just the average number of steps. And this is an expected value still. So depending on the policy, like the environment I was showing here, like this is still the stochastic environment where there's wind. So there's not like a single value of the number of steps. In general, there's some distribution over that. Right. So then the question is, what does the value function then look like in the case of discounting? So now we have these values of gamma. It's not just 1. So now, we have to look at the sum over gamma. And here, if you look at this expected value, this finite sum over gamma, there's just a formula for this. This is the formula for this sum of, gamma to the k over this range. And then, the only value here that needs the expectation is this gamma to the ns term, because all these other values, right, they're actually constants. So apparently this is what the state value equals, this equation. So it's no longer, right, it's no longer the expected value of ns. Now it's something which depends on the expected value of gamma to the ns. And, this quantity, like if you look at the expected value of n, right, as n gets larger and larger, right, this is a larger and larger negative number. So if you think about the different values this could take on, right, there's no bound to how negative this value can be. But if you look at, gamma to the ns for any gamma less than 1, as n goes to infinity, this quantity approaches 0, which means that no matter how long the episode takes, the contribution from that probability to the value is limited by this quantity, right? Now this blows up as gamma goes to 1, which makes sense because that it's unbounded just like it is in this case. But if gamma is 0.9 or something, this is just limited by 10. So, remember, like, we now need to compute this expected value of gamma to the n instead of gamma. And of course, this will depend on, right, what the distribution is of this n. But to make the problem a little easier to deal with, I'm going to just imagine that there is some, for a given state, there, like if I go back here, right, this is the episodic problem, setting gamma to 1. So what this value means is, like, from this starting state, the average number of steps to reach the goal is 21 steps. And all these over here, it's like 12, here it's 14. Okay, and that's because of, these wind values that make it, you can't guarantee reaching the goal that quickly. Okay, so now there's a value of negative 21. And now going back here, let's say that, there's some value, that there's some range, d around that. So actually, the ns values, like from a given state, there's an equal probability of reaching the goal, let's say, for ns minus d to ns plus d. Okay, so this is like the simplest probability distribution that you could have. So these are the probabilities of the different ns's, right? This is just, for the uniform distribution, these are all just integer values, right? So, then to calculate, so these are all equally weighted. And then, the expected value depends on summing these probabilities with the quantity that we're trying to compute, right? So in the case of gamma equals 1, we know that this was just ns. So here, this blue line, this is just showing, right, if like the average is 100, right here, and then this is showing all these values. Well, here the values are actually, there's a negative sign in front of all this. But so this is for ns equals 100, and then the expected value, component is just n, right? So this is just a straight line. And then you can see here, the expected value of n is just always going to match this average, which is 100. But then these red bars are showing the components of this quantity, which is, gamma to the n. Or, well, actually, what it's showing is this entire piece here, weighted. Yeah, well, it's just showing this quantity. So all of the individual values for each value of n. So at the value, of n equals 100, like you can see as you go out to larger and larger n, here, I'll set the discount right here. It's something I mentioned before, which is So around like 0.9 or something. So here, unlike in this case, these values are actually capped, right, at like close to -10, like I said here, right? And this is just because of the form of this, this expression of gamma to the n. So the important point here is that if I set like a given gamma, so let's say I had it before set at like, let's say I pick, some low value of gamma, like 0.7. And then I have the average value is 100. Now, here, I'll make this spread. So this is just saying that like on each side of that average, there's only, there's like a variability of 5 in each direction. And this is the discounted value, using this discount rate. But look, as I increase this spread, sorry, it's actually hard to see because these values are too small. Here, I'll make this a little closer to 1. So here we have, this discounted value is -37.96. As I increase the spread, right, you can see this value is actually, it's getting closer to 0, or it's increasing, right? And remember, our goal is to maximize the value. So what this is saying is that, for a given n, if we have some discount rate less than 1, and we had like, a very tight spread, then these are the contributions. And as I increase the spread, I'm increasing it symmetrically about 100. So now, it's adding some terms where, these terms are getting closer to 0, right, because these are episodes that end in a shorter time. And if this expected value is not affected by the spread, right? Like it's always 100, because for every value I add above 100, I'm also adding one below 100, and they're just averaging out to 0. It just stays here. But here, all of the really long, the high values of n I'm adding are less detrimental to the value than these values. And you can see if I start increasing this gamma closer to 1, this is eventually going to, right, all of these values are going to approach the values for the undiscounted case, which, should make sense. As gamma approaches 1, you're going closer to the undiscounted case. So the closer gamma is to 1, the less, effect there is on increasing variance. But, if I have a really small value of gamma, then these values are greatly affected by the variance. I mean, again, like, because the values themselves are small. And actually, that's not entirely true, because as you make gamma really small, another thing that happens is the values close to 0 also, like there's not as much of a difference getting close to 0. And I have another plot below this which shows that actually, even in the case of a uniform distribution, this relationship isn't like that straightforward. I mean, what is straightforward is that for any gamma, increasing this spread, while keeping the average value the same, increases the value, right? So this expected value of gamma to the n is benefited by, higher variance. And that is one of the reasons why, if you go back to this grid world example, you think, so like now, if I lower the value of gamma to something, you think like, well, why now is, the probability distribution is more spread out? Like there's a lot more, right? Like here, you can see these are the probabilities of being in these states, which are the closest like this path is the most straightforward path to reaching the goal. And these states, and now, increasing or lowering the discount rate, there's now, less and less. Well, now there's like no time spent here. And apparently now, it's favored to spend time in these states. And the reason why this is all changing is because these states actually might have, some smaller probability of reaching the goal very quickly. But in exchange for that, there are a bunch of other probabilities of taking a really long time. But those really long times, are not being penalized as much, right? Because, right, we're not like they would be penalized fully if gamma was 1. But, for any gamma less than 1, this is eventually going to limit out to some constant value. And yeah, we're basically saying, it's more important to have a smaller chance of finishing really quickly. And it's fine if in exchange for that, we take these longer episodes. Whereas in the undiscounted case, there would be no benefit to increasing this variance. Yeah, or certainly no benefit to increasing the variance in exchange for the average value getting lower. But, well, first of all, are there any questions about this, the difference between how, like, which expected value we care about? And how, like, basically optimizing the expected value of gamma to the n is not going to match up with, this expected value of just n itself.
So what is the distribution that's n representing the n of s?
N of s is like, for a given state, n sub s is the number of steps to reach the goal. Like in the grid world, here, like I said, it would be like 21. And then the expected value of that, like here, the expected value of n is 21 because this is undiscounted. But, this value of 21 doesn't mean that there's 100% probability of reaching the goal in 21 steps. It means that that is the average value. Whereas, when we have discounting and we're considering what determines the state value, well, it's not determined by the expected value of n sub s. It's determined instead by a function of the expected value of gamma to the n sub s. But here, this is like, this x-axis would be showing like, if the average value of n sub s is 100, then this is imagining a case where like all of these n values are equally likely, right? So then the expected value, like here, is determined by, taking the average of all of these values together. But the blue values here are the undiscounted values. And then, the orange values are showing the discounted values, but, as you change gamma, like here I'm showing, as you increase gamma, they approach the undiscounted values, as you would expect. And then, this text at the top of the graph is showing like the expected value, which corresponds to this n sub s expected value. And this other one is the expected discounted value, which is this equation. And the point is, as you change the spread, this value is unaffected. It's always the average. Whereas this value increases right here. So at 0, it's negative 82.5. And at this high spread, it's negative 78, right, which is a higher value. Or, so if there was a policy that produced the same average, but this wider spread, right, that policy would be favored by the discounted value.
Okay, so in the epicenter problem where it's basically a minus one, basically the NS is basically a measure where, because the actual function that we have is not the average visitations, but some expected value that depends on the discounted value. So that discounted value would affect the number of steps that would be expected, which I think that makes sense.
Well, the point of this is just explaining why, how with discounting, you don't get solutions that favor the shortest number of steps necessarily. That would be true if gamma is 1. But, right, if gamma is not 1, we're actually maximizing this quantity, which favors, higher variance in n. But if, if I tell you that, okay, so if I pick a certain average and I show you, okay, so depending on the distribution, like if there's no spread in NS, the discounted value is this. And if I increase the spread to the highest value it could be, then it goes up to this, right? So what that also means is that even if you have two policies and one of the policies, let's say, has a higher number of steps, like maybe it takes 101 or 102 steps on average, but it has a higher variance than the other policy, even that value could be favored. And here, so if you actually, here, what this is showing, this formula is showing what is this expected value of gamma to the n in the uniform case. Right, so here all the probabilities are 1 over 2d plus 1. And this sum, this is just the same finite sum. You can divide by gamma to the n minus d. It's just algebra, but you end up with this equation, right, where here d is this uniform spread, right, whatever it is. Like here, if it's 100, it's from 0 to 200. If n is 100. So your n is the average, d is the, plus or minus d is the spread in values. And then you end up with this formula for what the value function is in terms of this value of n and d at every state. Actually, this should be like n sub s and d sub s. Right? So you can express the value function here, and this is assuming whatever the policies are have this uniform distribution. But what this graph is showing, which is a little complicated, but this is showing for different values of gamma. And here I've set, so now like I've set the average at 50, or the big N here is 50. And then the spread is 0. So this is like, imagine we have a policy where from a given state, it takes 50 steps to reach the goal, and there's no variance at all. So what these lines are showing is that if we increase the average above 50, So here, like 1, 2, 3, this is saying if the average instead is 51 instead of 50, then how much higher does the D value have to be in order for this to have a higher discounted value? So it's saying if we can change the policy somehow by having, a slower completion on average, but, here this is like, so this is saying if gamma is 0.2 and we increase the average by 1, then if we increase D from 0 to 31, that would actually have a higher value. And it's like, again, like, so if you have gamma really low, like 0.1, then it looks like, we actually have to add a certain amount of variance. And as we increase gamma for a little bit, like here, this is 0.3, this is 0.4, the amount of variance we have to add to get that effect is lower to a point, right? It bottoms out here at 0.5, but then it also starts going up again, right? So for gamma equals 0.5, if we increase the steps by 1, we only have to increase D by 3. But then if you go back up here, this is now getting closer to 1. So at 0.995, we have to go back up to 35. So these lines, like there's not even a consistent pattern of how these lines follow, which is why what I was showing this graph earlier with the value changing. So according to this here, and I'll make it, if I make it 100, yeah, you can see more of the relationship here. And there'll be some gamma, like here, these lines start getting cut off, like this purple line, because this means that if you increase n by 4 instead of 3, then there is no variance that you could reach. Like the variance would have to be higher than is possible for this to be favored. And if gamma, so this line is disappearing as gamma approaches 1, meaning like the effect of favoring, like anytime this line exists here, it's saying that there is a scenario in which a slower average finish or a lower average reward is favored under certain conditions. Right. And that's what we see in this grid world where, as we change gamma, as we lower gamma, right, where now the policy is different from the average reward, we're saying in this case, the discounted optimum policy, right, is different from the optimum average reward policy. And, these values will have lower average reward than this policy. And the reason why it will accept a lower average reward, I mean, one of the reasons is this phenomenon, where you can get away with having a lower average as long as, you have a higher variance in the distribution. This is also saying that to have the strongest effect for this state, that would occur at gamma is 0.7. I guess if I go back here and set this gamma close to 0.7, right? Now we could see the difference. So, wait, this is at 100. Well, I guess maybe I mean, yeah, I don't know. It's hard to tell here why. So it went from negative 3.34 to negative, yeah, 3.28. But I'm not showing the exact same thing here. Because here I'm just showing a single average. But, this is saying like if I, but in this vicinity of parameters, right? Like here, the value is negative 3.34 and the average steps is 92. And if I increase this a lot, like, to 100, you think, oh, it'd have a worse value. But if I also increase the spread, right, this is now actually a higher value. So yeah, but it's just showing what's being shown here, which is like, yeah, like at gamma equals 0.7 in this case, like you could even have an average 88 steps worse than before, as long as you increase the variant or the D by 100. Yeah. So anyway, I know this might be a little confusing to get without like
Yeah,
deriving it yourself.
so it's essentially the relationship between the gamma and a distribution that you're using, which it seems like in your example you're using a linear distribution, which would be that parameter D, which would be a
A linear.
corresponding,
Well, it's a
the variance.
uniform distribution. Yeah.
Oh yeah, uniform distribution, not normal.
Yeah. I mean, I'm not showing it here because it's just a constant value, but it's just, you know, right. So if the average is 100 and the spread is 100, that just means that anything from 0 to 200 is equally likely. But yeah, this is showing. But anyway, the whole point of this is just explaining, how come in problems like this, where, superficially it seems like, oh, so the other consequence of this is that if I take away the stochastic, nature of the problem, so like I remove the wind, then the solution is unaffected by the discount rate. It will always favor the average, right? Because like if there is, let's say that there's no variability, right, in n. If there's no variability in n, then this expected value of gamma to the n is just gamma to the n, right? Gamma is less than 1, and this is, 1 minus gamma, right? So the higher value will always be favored by n approaching 0. Oh yeah, sorry. So this also gamma minus 1 is negative, right? This is the negative number. Oh, sorry. Do you have a question? Yeah. Sorry. Well, so this is like this V. I was like, this is the case where the reward is -1 per step, right? So the values are all negative. So if there's no distribution here, if it's just gamma to the n, then this always favors n as small as possible. And in the extreme case where n is 0, then the value is just 0, which is the highest possible value. Right. So yeah, this effect only happens in an environment where it is inherently stochastic, or it's not a deterministic environment. And actually, that was also a requirement for the average reward setting. So we had before, right? In order for this steady state distribution to exist and have these properties, and for this limit to exist, the environment has to be, this is what we talked about in the last training, but it has to be ergodic, or like the distribution has to exist, meaning, you can't have these deterministic sequences of rewards and states, because then that means that you can't replace this limit here, because this limit won't exist in that case. But then it's also true that, yeah, if you have absolute certainty over n, then you're back to the case where you always favor smaller n, which is also what is favored here, right? If the value in the undiscounted case, you always favor smaller n. So there's sort of, a combination of things that have to happen for the solution to depend on gamma. And one of them is that, the environment is stochastic somehow. It can also depend on gamma, for other reasons. Like here, there's a single goal we showed earlier. Well, not here, but if you introduce a secondary goal, here, I'll actually show that next example because this there is another problem in the book, which is one of the first. It's from chapter 3, but it's another one of these examples where um, the problem is very simple, but the optimal policy depends on gamma. And the reason why it depends on gamma is the same reason why this problem depends on gamma. So here I said, so this is another grid world example, but here it's a continuing problem, just like before, but it's a different shape. There is wind in this problem, but the wind is just uniform across the thing. The only reason why there's wind is to make the problem stochastic so that these distributions exist. So here, now there's two goals. And this is set up like this other problem in chapter 3, where the goal to the right has a reward of 1, and then the goal to the left has a reward. Well, here I can change it, but here it's set at 0.5. And then the goal to the right is 3 times farther away than the goal to the left. Or yeah. But since the problem is stochastic, it's not going to be, exactly like that. Okay, so this was another classic example of how the discounted solution can differ from the average reward solution. And this is more because of there's 2 different goal states. So depending on how far away you are from the goal, like, so here, what's being shown down here is the average reward solution. And the average reward solution, favors going to the right goal. And that's just because of, the wind values and how long it takes. But, apparently the way this is set up, going to the right has a higher average reward. And then here I've set this value of gamma, like this value of 0.952 happens to be the value of gamma at which going left and right is equally favored. And you could imagine, like, if I make gamma really low, then it's further discounting rewards that are further into the future, right? Penalizing them more. And here we're back to the case where there's, you just get that one reward at that future point. It's not like, there's no penalty per step. So I'll show here that if I make this gamma like 0.2 instead, then this is now going to completely favor the solution, right, where any state to the left of this mark, the policy is trying, to go left. And yet, the average reward solution is going to be unaffected, right? It doesn't use the discount rate at all. And then if I make this value very high, like 0.999, then this is going to eventually match the average reward solution, just like before. But here, there's actually, like here, right, like this state favors going to the right, but this state here favors going left. And I had shown that if you make gamma like really low, then even as far like out here, you're still favored to go left. And if I start making this value bigger, like this breaking point of where this transition happens is going to shift. Like here, it's still at that middle point. Let's see, where does it break again? Yeah, so here, so see how like these arrows all flipped? So the more I increase gamma, right, the more it pushes that transition point where it's favorable to go to the right goal. It pushes it more left, and eventually, it will match this case where it's all the way here. And the only time it's favorable to go left is when you're in these states, very close to the goal. So, I had said before, right, in the discounting case, when we solve this, um, all of the values are at their maximum possible value. So here, what I'm showing is the average reward solution, but I've also computed the discounted values, using this discount rate of whatever this solution is. And so here I set a value of gamma here so that these solutions don't match, right? Like the discounted optimum is going left and the average reward optimum is going right. And if what I said before is true, it would mean that if I compute the discounted values for this policy, all of these values should be smaller than all of these values, right? Because this is the optimal policy. And if you look at the values, right, these two boxes are showing the value function. So you can see if you look at every state for this policy, all of the values are higher, right? Like this 0.52 is greater than 0.45. The start 0.36 is higher than 0.21. This corner 0.88 is higher than 0.81. And that will be true, right, if you compare all of these. But remember that now when we're in the average reward setting, the thing that we're actually optimizing, I said towards the beginning, is this quantity, right? Which is even if we're using the average reward, the thing we end up optimizing is this average of the discounted reward averaged over mu. And mu is being shown here, right? So they have a different mu. And here in this little table, so this is showing, so remember, for this policy, all of the values should be higher, and they are. All the values are higher than this. And if I compute then the average value where I take all these numbers and I do a weighted sum of them by these probabilities, then what you see is that this policy has a higher value of J. Right? So even though all of these state values are lower than all of these, if you weight these over the distribution, you actually get a higher value for this policy, which makes sense because this policy is supposed to optimize J, whereas this is not. So what sort of seems like a paradox is like, how could a policy have a higher value at every state and have a lower value here? And the reason is because it only cares about the values, that are visited in this distribution. And you can see here, like both policies agree that like this corner or like these states around here on the right side have a higher value than these states over here. And the policy that goes to the right, spends more time in these states, which is why, this value of J is higher. And this also corresponds to the case where, optimizing J, where we actually care about, this average reward. I mean, here where by average reward, I don't mean this J where this is like the average discounted reward, but the average reward meaning, what we would care about in the limiting case of gamma approaching 1. But this was there was an example in the book, but I sort of turned the example in the book into this grid world example, but the example in the book also has these two branching paths. And there's this cutoff point you find where here, I found out what it was like 0.952, right? Where there's this break even point of gamma where it changes the policy. And here, you can actually pick the gamma where this is evenly split. Like here, we have no ability to do that. And even this policy, of course, has a lower value, right? This is the J value for this policy, and it's lower than the average reward policy. Again, because this should always have the highest values at individual states, and this should always have the highest weighted sum of those values across the distribution. So, are there any questions about that?
So, the comparison about, the discounted policy iteration and the average reward policy iteration seems to make sense given the comparison between the two of them of how the discounted policy eventually converges to the average policy when you set the discount as close to 1 when you have a system like this where you have essentially two goal states.
I'm sorry, two what states?
Two goal states.
Yeah. And this is like a slightly more obvious example of when the discount rate would matter, whereas like in the average reward case, they're like whatever solution is favored is going to be based on the construction of the problem, which in this type of problem, it's going to be based on, the average number of steps divided by the reward value. So basically, you would favor going left over right, if like 0.5 divided by the number of steps going left. I mean, here it's 0.5, so it's half. So if the time it took to get right was more than double the time it took to go left, then you would favor going left. And actually, it seems like it would be that case here, but the wind makes that not work. However, I think if I increase, can I make this 4? Yeah, so see now I made this 4. So I moved the right goal further away, and now it's far enough away that the average reward favors going left. See, because it's like the relevant value here, like even though the left reward is 0.5, the quantity that matters is 0.5 divided by the number of steps. So as I move the right goal farther away, right, the average reward for going to the right goal is lower. And eventually it's low enough that it's favored going left. And here it should actually be the case. But you can see that even though it's favored going left, like this policy is still different. Like it's not different from the start state, but it is different from out here, right? Because out here, eventually there's a point, or like even in these states where we should still go left. Whereas, in the average reward case, now it's saying from these states to go right, even though these states are actually never visited, right? Like, so technically, like these states don't matter from the perspective of this. And that's actually another, I'm trying to think now if that, I mean, the value should still be correct, even if the probabilities are 0. But, yeah, but I guess if I make this, let's see, if I make this gamma larger, it should still start approaching this. Yeah, so now these policies are matching, right? Yeah. So it doesn't, even though these states are not visited, this is still like the same as what the discounted solution says. But if I make gamma really small, right, like this point at which, Yeah, I mean, I don't even know if there's a point where it would flip even more of these over. But yeah, I mean, this kind of discount rate is also very unrealistic. Yeah, and if I make this even smaller, yeah. So this is an example of this like, yeah, two goal state. What I wanted to, um, sorry, let me just, here, might be easier to see if I write, um, some of this down. But, you know, in the case of discounting, right, if we have two different goals, we have like, right, like some discount rate gamma, and then this is like, would be like to the n1, and this would be like the g, um, like for going to state n1. And then if we have this alternative goal, oh, sorry, so this would be then like R1 versus R2, right? So if you want to see like which state is favored to go to, right? You basically like you would prefer to go to this goal if you have gamma n1 R1 is greater than gamma n2 R2, or you know, gamma to the n1 over gamma to the n2 is greater than R2 over R1, right? So this is for in the discounted case. So like this is the criteria to figure out like which goal it would head to, right? Where like so n1 is equal to distance to goal one, and then n2 is, you know, the same thing to goal two. But then in the average reward case, right, it's different because in that case we only care about right R1 divided by N1, right? Because like this is the average reward. And you can see like just like in the other math I was showing, it's just a different calculation. Now there may be a value of gamma for which these two things match, right? In the case of like this specific problem having two goals. And if we pick gamma, right, as gamma approaches one, right, then this, right, this criteria will match this criteria. You can you can show that somehow, or like there's always for whatever this is, there's some value of gamma close enough to one that it favors the same thing as this, which is sort of what you see here. As I make gamma close to one, you know, again, like there's always some point at which the policies will match, right? But is this, I mean, this is just again like previously I was showing the like the stochastic case where there's not even two goals, but where like you'd favor a different type of policy. And this is showing like this is just a fancier way of this problem where you decide whether to go right or left. And it's just showing, you know, where is the breaking point of going right or left. And you know, why does it seem like, I mean, it also raises the question of, you know, for this type of problem, which policy should we care about? You know, like should we care about the one that favors the average, or you know, should we take gamma close to one? But anyway, that's just these grid world examples. The thing that is, you know, the actual example used in the book for this average reward case is here, I'll skip this mountain car thing, but is this access where is the example? This access control queuing task. And I'll just show in the book where this task is described. This problem. So had this written down. It might be easier to see on here, but so this is a problem where you have like a set of servers numbered from 1 to 10. And then there's this queue of customers. So basically there's like a list of customers. You can only, like at any point, you're going to take the top thing off the queue, and there's a list of priority values. And these priority values are basically like what the customer would pay for getting access to the server. So they're also whatever reward value you get. So at each point, you can choose to accept or reject a customer. And if you accept a customer, there has to be an available server to accept them. And then they end up taking up a server, and you get this reward value, for whatever. And you're able to see what their priority value is. And then the other part of the problem is that if servers are occupied, then they become free with a 6% chance on every step, right? So then if all the servers are occupied, we can't actually accept a new customer. So it has to be rejected, and you would have to wait. And then, you can look at these probabilities and say, if all the servers are occupied, then what is the chance of them all being occupied on the next step? And that's 54%. And then there's a bunch of these other probabilities that you could calculate. But this task ends up being solved in the book with one of these sampling methods, although we don't have to do approximation. But the point of this task is like, as you accept customers, the servers get filled up. And that means that you can't accept a new customer if they happen to all be full. And if the new customer you get is like one of these high priority customers, then you're basically losing money. So the idea is, let's say that these priorities will occur with a uniform probability, like there's an equal chance of seeing any one of these. Then what should the policy be? Depending on how many servers are occupied and what priority the new potential customer is, what should you do? And it's not as simple as just always accepting a customer, because that's not going to be as good as doing, other things. And, actually computing all these probabilities without, the techniques like these reinforcement learning techniques would be very difficult. And you'd have to think about like all of the future ways in which servers could be freed and new people could arrive. Luckily, we don't have to worry about that, because we can just set this problem up as, an MDP like I've done here. And this is just doing it as like a problem with sampling. So we have servers, and this is just computing like a step, which is just, it takes, it sees how many servers get freed on the next step. And then if we accept a customer, it checks like that can only happen. And then if we accept a customer, the number of free servers will go down by 1. And then, any of the servers that were already occupied could get freed with some probability. So that's just what this does. We don't actually need to do approximation because there's a finite number of states here, but we can do state aggregation and still use the approximation techniques, where we're using the approximation technique, but we're actually computing a distinct value for every state. Here, this is showing, I'm using state aggregation where, each state is defined by the number of free servers, and then what is the priority of the next customer in the queue. So, you can think of that as just a matrix, and you can, assign an index to all the states. And that's what I'm doing here. And then we can use what was introduced in the book of this, computing using this differential semi-gradient Sarsa to compute the value. And here, what's going to be optimized is the average reward, which is like the average, priority that we are able to accept and collect money for. And this is a continuing problem, so the problem just goes on forever. And there will end up being some long-term distribution of how many servers are available. So this is just showing it. This should match up with what's in the book of the solution. So apparently, when you solve this with this Sarsa technique, this is the solution you find where this region of the state space, you reject new customers. So obviously, if a customer has the lowest priority, they are rejected the most frequently. And then apparently, if a customer has the highest priority, you always accept them if you can, which does make sense because, why would you not accept the highest possible priority? I mean, there might be the only reason to not accept a lower priority is you could see one of these people later. So this is showing these differential values where, obviously, like it's always better. I mean, it's always better when you have more free servers and the priority of the next person you're seeing is higher. But really what's important here is policy. As you run this, you also are keeping track of a running total of what you expect the average reward to be. And that's what's shown here in the pseudocode is that this value of R bar is this running total. And this is the thing that if this is converging properly, this should increase in time. So this is showing as you run this, the average reward appears to be going up, and it ends up being about 2.6 at the end of this process. So following this policy seems to produce an average reward of 2.6. In this case, like the priority values are 1, 2, 4, and 8. So, it's sort of a little bit, I mean, it's actually not even as good as the average, or the average value is much higher than 2.6 of priority. So apparently we're unable to create a policy where, or like let's say you always waited for priority 8 to accept. Doing that is not even going to produce a reward higher than this. So that's using, the Sarsa technique. It turns out like because this is, even though this is a stochastic problem, it's stochastic because the next customer that comes, their priority could be anything, any one of these values. And also there's this 6% chance of freeing up a server. But we can still calculate a full distribution of transition. So here, the step function I'm using, right, is I'm just, I have this rand function and I'm just freeing up a server. And also I'm selecting a random priority, right, for the next step. In this function, I'm actually computing the probability of all of like the next step, how many servers would be free. The probability is, it's based on, both a certain number of servers being freed and a certain number remaining occupied. And then, there's this factorial, which is computing the multiplicity of that probability. So this ends up computing this distribution. The distribution over the next priority is straightforward because that's just, all of the priorities from all 4 of them are equally probable. So you can end up, computing this distribution. And here I'm showing, this is showing for if you have 0 free servers, they're all occupied, then this is the probability of how many are free on the next step. Right. So the highest probability is that none of them are free. And then, it goes, this is the, then there's some, diminishing probabilities of more of them being free. And this is showing, depending on how many are free, right? This is like if there's 4 free, and this is like if you accept or reject the next customer, how many will be free on the next step. Obviously, in this case, they're both the same because we can't accept a customer when there are no free servers, so there's no difference. But if there are free servers, accepting, you know, low, like this adds a probability that only 5 will be free on the next turn. Whereas if we reject the customer, there's a 78% chance we'll still have 6, and then a significantly higher chance there'll be 7 free servers than in the case where if we accept someone. So does this all make sense, like how the task works? Well, I guess I didn't. Like this is the solution that the book computes is just through sampling. But then you see how like it's not actually that, like we can actually calculate these probabilities of the transition. Because the advantage of having these probabilities is that we can apply like the same sort of technique I was using here, where I can actually use like dynamic programming to compute the policy. The only reason I did that is because, well, there's sort of 2 reasons. One is that we can actually solve this problem as a discounted problem instead, right? In which case, again, because it's a stochastic problem, the optimal policy now also depends on the discount rate, right? So if I make the discount rate close to 1, other than these numerical problems, we should end up approaching the policy we had before. But if I start out with a very low discount rate, well, that one is too low. Let's see, okay, so at this discount rate, where, yeah, so this is like discounting future rewards the most. So it prioritizes things that happen closer to the present. Then, we accept everything. In fact, the only rejection would be if there's only one free server and we get the lowest priority person. And then as we increase the discount rate closer to 1, we end up rejecting more. So like here, now it favors, well, now, you also want to reject even 2. And now you want to reject 1 also, even if there's 2 free servers. And over time, you eventually approach this solution that we had before. You can see that the actual relationship with the value should be the same, right? There's actually a comment in the book that these values should not drop off as we go out here, because as there's more and more free servers, like that's even better than this case. And the reason why this drops off, if we're solving this with Sarsa, is that we're collecting samples, and I'll show that we never end up sampling these states, so they never get updated. But you can see here, like the value should increase as the number of servers are free. Okay, so apparently, like, again, we have another solution where, it does depend on gamma. And this is showing the same sort of dynamic programming solution, but we can apply it also with average reward. So this, unlike what's in the book is solved with a sampling technique, what's being shown here is the actual true solution of this problem. And actually, these rejections of priority 1 should go all the way out, right? Clearly, these values are not correct, going out here to 6, 7, 8, and above free servers, which is why the value or the policy doesn't get updated. But here, if you actually solve this exactly, these rejections should happen all the way out here. And then these are what the value should be if we don't have this sampling problem. This is showing, because when you solve it in this way, you also end up solving for the steady state distribution. And this is showing that you basically never see these states where we have, oh, sorry, this should be, okay, sorry. This should be 0 to 10 for free servers, not 1 to 11. But you basically never see these states where you have like this many free servers when you are following this policy. And the average reward is approaching this value of 2.67. So again, like this is policy iteration, but as you would expect, like for the policy to increase over time, or for the average reward to increase over time.
Well, that seems to make sense, the steady state distribution, since you should want to, optimize the amount of servers being used. And so if you have a bunch of unused servers, that doesn't, that seems like, poor use of resources. Of course, it
Yeah,
seems
like,
kind of bad that all the priority one states are basically being rejected.
yes, apparently in this problem, priority one is always rejected. And as a result, I mean, another sort of interesting thing is that the state that is most common to be in is one in which there are three, or this should be two. Yeah, two free servers. Sorry. Yeah, this should be, yeah, because this should be 0, not 1. Yeah, so the most common state to be in is one in which there are two free servers. This, I don't even know if this is symmetric. This isn't even symmetrical, I don't think. Yeah. Yeah, but depending on the parameters and what the priority values are, this would be different. But, this is to optimize average reward, which is what happens when we make gamma approach 1. But, we still have this issue, like, even if we make gamma like 0.9, then, this is the optimal policy. And it's like the same thing I said before, where like we are optimizing just a different, that there's a different objective here. And, for this task, we could solve it, either way. And if you do want, like the only way to actually get the exact solution for the average reward of this is to do this average reward solution. Because, right, if we try to compute it like with this one, and we try to increase gamma, we sort of get something that approaches that solution, but there's only so close we can get to gamma equals 1. Right? Like, and then we start getting these numerical problems where we don't have a preference. Like these gray values represent being indifferent to either accepting or rejecting the customer. And yeah, I guess which solution is most relevant to you? It it is sort of a matter of preference, but I mean the average reward is pretty straightforward, right? Like what it means in this problem. It's like, if we take this, at least if we define it like the way it was in the book originally, um, where we're actually like averaging it through time, right? But it's also just the average reward per step, or it's the expected reward per step in this problem. And if it's money, this would just be maximizing the average money collected on every step, which seems like it would be what you want to do. But, another way of looking at money, and depending on how long this process goes on for, like let's say this process is going on, for years or months, and then, the money you earn, you could invest it and earn interest or something. In that case, it actually might be more relevant to not figure out the average reward, but to do this discounted reward, because then, this is actually penalizing money you earn in the future, depending on the value of gamma, that's how far it is into the future. But probably the only time where you could like definitively say, oh, that's the correct like solution technique to use for this is if you actually like had a situation with money and you knew you could do something with that money, like, through time or invested or earn interest on it, then in that case, you would probably favor using the solution with discounting. But you would have to make sure that the gamma you picked, was appropriate. And setting gamma to one or doing the average reward case is basically just saying, like there's nothing useful I can do with the money, or maybe you have to spend, the money immediately and you never like hold on to it, in which case, yeah, you wouldn't care about, favoring receiving money in the present to receiving money in the future. But, usually with money, it's like you would want to use a discount rate because, there's inflation. Like there's many reasons why you would discount future money in some way. But in the case of a grid world problem or something, yeah, like there's no obvious connection to anything like that. But I'd say like the connection between using a discount rate and having, yeah, that connected to actually like doing something with monetary value is probably the best justification for using a particular discount rate. Otherwise, when you have problems, and you see that the solution really does depend, like in this grid world case, where it does depend a lot on the discount rate, it does beg the question of like what discount rate should you use? And oftentimes you might not have a good answer for that, like you would in a case where, it clearly has some monetary meaning. And that's where, it starts getting a little uncomfortable where like you don't just want to pick some discount rate and see what happens. If it really does like change the nature of the problem, unless you have, a good reason for it. But that is another motivation for introducing this average reward in the first place is that, if you have a problem where you think, the average reward is the relevant, metric that you care about, then you can use this technique and completely forego with using the discount rate. So, I mean, those are all that's like the example actually solved with the Sarsa technique in the book. There were, yeah, other exercises which are pretty, like pretty math heavy, and they do illustrate some of these same points about these problems that like aren't ergodic or what can you do with them. I do have it like in the notes if you check the website and want to read the solutions. I think like they are pretty good exercises and worth looking at, but also a lot of the concepts of what I was computing here, I went over in this the grid world example and showing some of the other math. So I don't know. We can maybe, I mean, I could go over them if people want me to, or I guess the most important ones are the 10.6 and 10.7, but otherwise we can probably, move on to the next chapter. Yeah, I don't know. I kind of, yeah, tried to cover the average reward thing pretty thoroughly. So it's just up, it's more of like what speaks to you more of like for some people, these exercises might reveal the important points of how average reward works more than, what I went over with these examples or with the math I showed of that distribution. Yeah, I guess maybe I'll say maybe just one more thing about this average reward, which is that this new G was defined with these differential value functions. And remember, the weird thing about the average reward setting is that these differential value functions, the values are not being optimized, right? Because these all have this R average reward baked into them. And again, like this G has this average reward baked into it. So we define these and use them to find the solution. But the thing that's being optimized is the average reward here. And all the techniques end up making this increase over time as we solve it. And this quantity, which is the differential return, looks like something. It's like we're taking the reward at every step and we're subtracting the average reward. And it looks like this should be 0, right? Because like as you go out, and we know this steady state distribution exists. So as we go out to these faraway time steps, we had already said that we expect these rewards, like this expected value exists, right? So as we go out to far enough time steps, we can look at this sum and just replace it like with 0 far out here. Because in the long-term limit, all of these values, as we average them together, they're just going to equal r pi, and we're subtracting r pi. So this is 0. So really, what these differential returns are what is the impact here of like S? What is the impact of being in a state S on these early rewards as they compare to the average? Right. So this is a statement really only about the immediate behavior of being in a state rather than, because what happens long term, we already know, is that these rewards just approach r pi. So, all these differential values, which is this is how we find the optimal policy, is, a higher value means that, this state has higher early rewards than average. And that, obviously like states, if it's a maze problem, states close to the goal have higher, rewards than average because they're close to the goal. And then, so we can still use the value function as a way to, to move towards states with higher value. But, they don't actually represent like the same thing as they did before. They're not being optimized. They're just a way to track the relative values, where the relative values are really, the early components of this sum and how much the rewards exceed the average. And then, like I showed here, or maybe I showed it in the grid world. Or no, I did show it in the access control problem. Where, as this is being solved, the average reward is what is, increasing through time. And the differential values are just, just a way to track where we should move in the state space, but don't actually represent anything, any absolute value. So are there any more questions about this chapter or anything? Or any, yeah, because for next time, say we could either move on chapter 11, which is pretty much entirely like mathematical and like has some interesting theoretical stuff. Or I can go back over, I guess, those, yeah, a couple of those exercises if you want. So it's up.
I'd be up for moving on to chapter 11. This feels very thorough on chapter 10.
Okay, yeah. So if anyone does want to see the solutions to these exercises, again, like you can just check the notes, or it should all be linked in the meeting description and the other places. But yeah, you can see. And there was one other thing I think in the notes, I put it mostly, but there's another derivation, or I tried to make, showing that as I believe this is true, I'm not completely sure, but I believe that for any continuing problem, in the limit of gamma approaching 1, that it should always match the average reward solution, as long as the criteria exists, like the steady state distribution exists and all those other criteria for the average reward. It's a little, yeah, I'm not sure, like it's sort of a hand wavy proof, but the basic idea is that as gamma approaches 1, the discounted value function approaches this quantity, which only depends on the average reward. And that's what it's similar to the other proof. But if it is true, and I believe it is, then it should match up with what we were saying, that, if in fact you're going to take the limit of gamma going to 1, then you should just solve the problem with the average reward technique, which you could do either with the SARSA or with a tabular problem, because that way you don't have any numerical, instability problems from gamma approaching 1. As I showed, the state values end up diverging as you get close to that. So yeah, it's more straightforward to solve with average reward. So, okay, next time we can start chapter 11, which is going to be, it's one of these asterisk chapters, so it's not even, like we could skip it and go to chapter 12, but it is like very theoretically rich and kind of, somewhat confusing, but hopefully by the time we get to it, I'll have a little more insight into it. I hope I definitely was not completely sure of all the nuances of the average reward before going through this. So hopefully now it makes some more sense. And if not, hopefully if you read the notes, it'll clarify everything.
Thank you so much, Jason. This was awesome.
Okay, well, thanks for coming, everyone, and hopefully see you next time.